Good evening. Thank you very much for tuning in to my channel. If you like it, please consider hitting that button, and please take a look at some of my other videos as I cover similar topics. You might be able to see that I'm interested in electronics, microcontrollers, radio, and related subjects. What I like doing is learning. It's one thing to be all practice and no theory, and then there's the other end of the spectrum where you can be all theory and no practice. Anyway, I found this book on Google Books. It's called Antennas and Wave Propagation by U.A. Bakshi and A.V. Bakshi and K.A. Bakshi. So this might be brothers or brothers and sisters. This is a family effort, which is interesting to see. So I'm going to read this. There's a lot of math, so all credit goes to the Bakshi family, and I appreciate what they did and what they created. So that's a lot of talking. So when I open this book on Google Books, it's a limited preview, but the first 100 pages I think is covered. So I skipped the table of contents, and I'm just going right to the introduction. And that is on page, let's see, page 1. And it's talking about antenna fundamentals. So I will just read. Introduction. The electric charges are the sources of the electromagnetic EM fields. When these sources are time varying, the EM waves propagate away from the sources and the radiation takes place. In general, the radiation can be considered as a process of transmitting energy. The radiation of the electromagnetic wave into the space is effectively achieved by using a conducting or dielectric structures called antennas or radiators. In general, antenna can be defined in a number of ways. A metallic device used for radiating or receiving radio waves is called antenna. According to IEEE standard definitions of terms for antenna, it is defined as a means for radiating or receiving radio waves. Thus, antenna is regarded as a transition between the free space and a system used for launching an electromagnetic waves. The system used for launching the electromagnetic waves is either transmission line or waveguide. The antenna, as a matching device between free space and the wave launching system, is as shown in figure 1.1, and there's a simplified diagram it looks, and the caption says figure 1.1, antenna as a matching device between free space and wave launching system. And I will read the words in the picture. It shows a source, then it shows transmission lines, then it shows antenna, and there's these radiating patterns coming off. I just describe what I see. That's what I'm trying to do. Antenna can be used as transmitting antenna or receiving antenna. It has directional properties. It is the important component of a wireless communication system. Page 1-2. Let us study different types of antennas. Some of the important types of antennas are wire antennas, traveling wave antennas, slots and aperture antennas, reflectors, and lenses. Integrated circuit type antennas. The typical antennas are as shown in the figure 1.2. And so I will read them. A. Dipole. B. Loop. C. Helical. D. Rhombic. E. Dielectric. F. Pyramidal horn. G. Parabolic dish reflector, which in the picture shows reflectors, radiating dipole, and a coaxial feed. H. Microstrip patch antenna. I. A coplanar strip horn. Figure 1.2 was the title of this picture, and it's called Typical Antennas. Page 1.3. The most commonly used antenna is the dipole antenna, as shown in the figure 1.2a. It is made up of two straight wires or conductors laying along the same axis. The exciting source is kept at the center. With an exciting source at the center, a symmetric dipole is produced. In general, the dipole antenna is excited by a voltage obtained from a transmission line, waveguide, or directly from generator. The loop antenna, as shown in figure 1.2b, consists a single turn or many turns of wire forming a loop. It is generally excited by a generator directly. The field produced by a loop antenna is very much similar to that produced by a small dipole. The antenna, with a wire in the form of a helix backed by a ground plane, is called helical antenna. The helical antenna is as shown in the figure 1.2c. All the three types of antenna mentioned above are wire antennas, which are extensively used in aircrafts, ships, automobiles, etc. In case of a traveling wave antenna, the antenna is designed in such a way that a traveling wave in one direction is obtained. The velocity of this wave equals the velocity of light, and it excites the waves in the space in the same direction strongly. Thus, the maximum directivity can be achieved. The rhombic antenna, shown in the figure 1.2d, is the common example of a traveling wave antenna. When only one half of the antenna is utilized, the antenna is called the antenna. The traveling wave antenna, in which the traveling wave is guided by a dielectric, is called dielectric antenna. In dielectric antenna, near cutoff, the phase velocity equals the velocity of light. The fields produced extend outside a dielectric guide. These outward fields excite the desired radiation in space. Such traveling wave antennas are useful for broadband signals. In general, a field across an aperture excites radiation in space. If an aperture is small, it must be resonant to excite large amount of power. But if an aperture is large, it need not be resonant. The common example of aperture antenna with larger aperture is, I better start that again. I'm just going to start that paragraph again. In general, a field across an aperture excites radiation in space. If an aperture is small, it must be resonant to excite large amounts of power. But if an aperture is large, it need not be resonant. The common example of aperture antenna with larger aperture is horn antenna, as shown in the figure 1.2f. The horn antenna is tapered at one end, which provides a transition between guiding system and surroundings. It is also commonly known as electromagnetic horn. The aperture antenna is also useful for the broadband signals. For the microwave radiation, the parabolic reflectors are most common used. The parabolic reflector, illustrated in the figure 1.2g, is based on the principle that the electromagnetic waves are reflected by a conducting sheet. The dish of the parabolic reflector acts as a mirror, and it reflects the radiation from a dipole or horn placed at the focal point. Then the exactly parallel beams are resulted. This type of antenna is most suitable in radars, communications, astronomy, etc. The antenna to be used with microwave integrated circuit may be placed on a dielectric substrate. The figure 1.2h shows an integrated circuit type antenna in microstrip form. The figure 1.2i shows a horn type antenna used with an integrated circuit. As antenna is placed on a dielectric substrate, the integrated circuit type antenna is also called patch antenna. Page 1.4, radiation mechanism, which is 1.2 is a paragraph. Consider different basic sources of radiation one by one. 1.2.1, single wire. It is a fundamental single wire antenna. Then, by the principle of radiation, there must be a time-varying current for a single wire antenna. If charge is stationary, no current is developed. No radiation is observed. If charge is moving with uniform velocity, then no radiation for straight wire, which is infinite in extent. 2. Possible radiation if wire is curved, bent, discontinuous, terminated, or truncated. A shows truncated, B shows terminated, C shows discontinuous, D shows bent, E shows curved. Radiation from single wire. 1.2.2, 2 wires. Consider an antenna driven by transmission line with a voltage source connected as shown in the figure 1.4a. When the source is applied, the electric field gets developed between conductors. The electric lines of force are tangent to the electric field. The strength of electric lines of force is proportional to the electric field intensity, as the free electrons have tendency to get separated from the atom. The electric lines of force operate on free electrons of each conductor and force to displace. Due to the charge movement, current is produced and it produces magnetic field intensity. The electric field lines travel from positive charges to negative charges, while the magnetic field lines form closed loops encircling current-carrying conductors. The charge distribution is due to electric field lines, assuming sinusoidal voltage source between the two conductors. The electric field between the conductors is also sinusoidal. Page 1.5. Well, this is diagram A, which I suppose was just explained. And then there's diagram B, and this shows radiation from 2-wire antennas. (1.2.3) Dipole. Consider a small dipole antenna where time of travel is negligible. Consider that a small dipole is center-fed in the first quarter of the period t, i.e. t equals t divided by 4. This is the time at which the charge attains maximum value. At this instant, the lines travel radially outward. Okay, I think I'm going to stop it here, simply because I didn't quite comprehend everything I read, and so I'm forced to actually go find definitions of what's just been explained, or to seek for explanation elsewhere regarding the basics of antennas. Okay, so I won't get rid of the reading I just read, but I'm going back to the basics. So I went to Wikipedia and I typed in antenna, and now I am just going to read that. Now, a lot of different definitions. Antenna, radio. In radio engineering, an antenna is the interface between radio waves propagating through space and electric currents moving in metal conductors, used with a transmitter or receiver. In transmission, a radio transmitter supplies an electric current to the antenna's terminals, and the antenna radiates the energy from the current as electromagnetic waves, radio waves. In reception, an antenna intercepts some of the power of a radio wave in order to produce an electric current at its terminals that is applied to a receiver to be amplified. Antennas are essentially components of all radio equipment. An antenna is an array of conductors, elements, electrically connected to the receiver or transmitter. Antennas can be designed to transmit and receive radio waves in all horizontal directions equally, omnidirectional antennas, or preferentially in a particular direction, directional, or high gain or beam antennas. An antenna may include components not connected to the transmitter, parabolic reflectors, horns, or parasitic elements, which serve to direct the radio waves into a beam or other desired radiation pattern. The first antennas were built in 1888 by German physicist Heinrich Hertz in his pioneering experiments to prove the existence of waves predicted by the electromagnetic theory of James Clerk Maxwell. Hertz placed dipole antennas at the focal point of parabolic reflectors for both transmitting and receiving. Starting in 1895, Marconi began development of antennas practical for long-distance wireless telegraphy, for which he received a Nobel Prize. That concludes the first paragraph, and then there's a next paragraph called Terminology, which I will read now. The words antenna and aerial are used interchangeably. Occasionally, the equivalent term aerial is used to specifically mean an elevated wire antenna. The origin of the word antenna relative to wireless apparatus is attributed to Italian radio pioneer Marconi. In the summer of 1895, Marconi began testing his wireless systems outdoors on his father's estate near Bologna, and soon began to experiment with long wire aerials suspended from a pole. In Italian, a tent pole is known as l'antenna centrale, and the pole with the wire was simply called l'antenna. Until then, wireless radiating, transmitting, and receiving elements were known simply as terminals. Because of his prominence, Marconi's use of the word antenna spread among wireless researchers and enthusiasts, and later to the general public. Antenna may refer broadly to an entire assembly, including support structure, enclosure, if any, in addition to the actual functional components. A receiving antenna may include not only the passive metal receiving elements, but also an integrated preamplifier or mixer, especially at and above microwave frequencies. And then there's another paragraph called Overview. Antennas are required by any radio receiver or transmitter to couple its electrical connection to the electromagnetic field. Radio waves are electromagnetic waves which carry signals through the air or through space at the speed of light with almost no transmission loss. Antennas can be classified as omnidirectional, radiating energy approximately equally in all directions, or directional, where energy radiates more along one direction than others. Antennas are reciprocal, so the same effect occurs for reception of radio waves. A completely uniform omnidirectional antenna is not physically possible. Some antenna types have uniform radiation pattern in the horizontal plane, but send little energy upward or downward. A directional antenna usually is intended to maximize its coupling to the electromagnetic field in the direction of the other station. A vertical antenna, or whip antenna, radiates in all directions horizontally, but sends less energy upward or downward. Similarly, a dipole antenna, oriented horizontally, sends little energy in direction vectors parallel to the conductor. This region is called the antenna null. The dipole antenna, which is the basis for most antenna designs, is a balanced component with equal but opposite voltages and currents applied at its two terminals. The vertical antenna is a monopole antenna, not balanced with respect to ground. The ground, or any large conductive surface, plays the role of the second conductor of a dipole. Since monopole antennas rely on conductive surface, they may be mounted with a ground plane to approximate the effect of being mounted on the Earth's surface. More complex antennas increase the directivity of the antenna. Additional elements in the antenna structure, which need not be directly connected to the receiver or transmitter, increase its directionality. Antenna gain describes the concentration of radiated power into a particular solid angle of space. Gain is perhaps an unfortunately chosen term, by comparison with amplifier gain, which implies a net increase in power, period. In contrast, for antenna gain, the power increased in the desired direction is at the expense of power reduced in undesired directions. Unlike amplifiers, antennas are electrically passive devices which conserve total power, and there is no increase in total power above that delivered from the power source, the transmitter, only improved distribution of that fixed total. A phased array consists of two or more simple antennas which are connected together through an electrical network. This often involves a number of parallel dipole antennas with a certain spacing, depending on the relative phase introduced by the network. The same combination of dipole antennas can operate as a broadside array, directional normal to a line connecting the elements, or as an end-fire array, directional along the line connecting the elements. Antenna arrays may employ any basic omnidirectional or weakly directional antenna type, such as dipole, loop, or slot antennas. These elements are often identical. A log periodic dipole array consists of a number of dipole elements at different lengths in order to obtain a somewhat directional antenna having an extremely wide bandwidth. The dipole antennas composing it are all considered active elements, since they are all electrically connected together and to the transmission line. A Yagi-Uda antenna, or simply Yagi, has only one dipole element with an electrical connection. The other parasitic elements interact with the electromagnetic field in order to realize a directional antenna over a narrow bandwidth. There may be a number of so-called directors in front of the active element in the direction of propagation, and one or more reflectors on the opposite side of the active element. I'll read that last sentence again. There may be a number of so-called directors in front of the active element in the direction of propagation, and one or more reflectors on the opposite side of the active element. Greater directionality can be obtained using beam-forming techniques such as parabolic reflector or a horn. Since high directivity in an antenna depends on it being large compared to the wavelength, narrow beams of this type are more easily achieved at UHF and microwave frequencies. At low frequencies, such as AM broadcast, arrays of vertical towers are used to achieve directionality, and they will occupy large areas of land. For reception, a long beverage antenna can have significant directivity. For non-directional portable use, a short vertical antenna or small loop antenna works well, with the main design challenge being that of impedance matching. With a vertical antenna, a loading coil at the base of the antenna may be employed to cancel the reactive component of impedance. Small loop antennas are tuned with parallel capacitors for this purpose. An antenna lead-in is the transmission line or feed line, which connects the antenna to a transmitter or receiver. The antenna feed may refer to all components connecting the antenna to the transmitter or receiver, such as an impedance matching network in addition to the transmission line. In a so-called aperture antenna, such as a horn or parabolic dish, the feed may also refer to a basic radiating antenna embedded in the entire system of reflecting elements, normally at the focus of the parabolic dish or at the throat of a horn, which could be considered the one active element in that antenna system. A microwave antenna may also be fed directly from a waveguide in place of a conductive transmission line. An antenna counterpoise or ground plane is a structure of conductive material which improves or substitutes for the ground. It may be connected to or insulated from the natural ground. In a monopole antenna, this aids in the function of the natural ground, particularly where variations or limitations of the characteristics of the natural ground interfere with its proper function. Such a structure is normally connected to the return connection of an unbalanced transmission line, such as the shield of a coaxial cable. An electromagnetic wave refractor in some aperture antennas is a component which, due to its shape and position, functions to selectively delay or advance portions of the electromagnetic wavefront passing through it. The refractor alters the spatial characteristics of the wave on one side relative to the other side. It can, for instance, bring the wave to a focus or alter the wave front in other ways, generally in order to maximize the directivity of the antenna design. This is the radio equivalent of an optical lens. An antenna coupling network is a passive network, generally a combination of inductive and capacitive circuit elements used for impedance matching in between the antenna and the transmitter or receiver. This may be used to improve the standing wave ratio in order to minimize losses in the transmission line and to present the transmitter or receiver with a standard resistive impedance that it expects to see for optimum operation. And that concludes that paragraph. And there's all kinds more paragraphs that can be read. Well, I'm certainly not an expert, and I love saying that. Take the pressure off me. I didn't understand a lot of that, and so I know I'm going to have to put some effort into studying what I just read. So I will be putting some pictures to the text that I just read, and it will be to the best of my ability. They may not be perfect, but it'll help in maybe understanding the reading. Okay, thanks for listening, and I may create a glossary video after this.